Hello, and welcome to Using Fundamental Identities, and I probably should include fundamental trigonometric identities. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1508 Pre-Calculus at UTEP, Chapter 5, Analytic Trigonometry. It comes to us from Larson's 10th edition pre-calculus text. Section 5.1, Using Fundamental Identities. So we've had these identities before in Chapter 4, but if you're watching these one at a time, here we go. Here's some reciprocal identities. Keep in mind that the sine and the cosecant are reciprocals of each other. The cosine and the secant, reciprocals of each other. And the tangent and the cotangent, reciprocals of each other. If you need to write these down, here's a great time to hit pause. We also have quotient identities. When we use the unit circle, we define sine to be y and cosine to be x. Tangent was y over x. When we used right triangles, we said sine was opposite over hypotenuse, cosine was adjacent over hypotenuse, and tangent opposite over adjacent. So in everything we've done, the tangent of u is always sine of u over cosine of u. And since we have a reciprocal for cotangent, cotangent of u is cosine of u over sine of u. Quotient identities. Our Pythagorean identities, our main one, sine squared u plus cosine squared u equals 1, comes to us from the unit circle. And then the next two, the one where cotangent and cosecant and tangent and secant are paired up, if we divide this original equation by sine squared, we'll get the first equation. If we divide this original by cosine squared, all three terms, we'll get the third Pythagorean identity. Again, if you need to write them down, hit pause. We also have cofunction identities, and I gave you a brief glimpse into this in graphing the other four trig functions, showing that cotangent that's shifted is just the graph of tangent. But this is exactly what it means to be a cofunction. They're off by pi over 2, so a little shift and we're good to go. Even and odd identities, keep in mind that the cosine and secant functions are even, therefore cosine of negative u is positive cosine of u, whereas sine, cosecant, tangent, and cotangent are odd functions, therefore the tangent of negative u is negative tangent of u. So even functions in the middle, odd functions around the outside. Let's use these. We're going to use the given values to evaluate, if possible, all 6 trig functions. I know that the tangent of x is square root of 3 over 3, and the cosine of x is negative square root of 3 over 2. I know that tangent is positive in quadrants 1 and 3. I know that cosine is negative in quadrants 2 and 3, so they overlap in quadrant 3, and I draw an angle in quadrant 3. The cosine probably gives me more information. You can see that this is probably rationalized, whereas this one is not. The cosine of x is negative square root of 3 over 2. Well, I know that in quadrant 3 the x value is negative, so a negative square root of 3 over 2. And if I wanted to verify and make sure that this was in fact a rationalized denominator, I could unrationalize, or I could just use the Pythagorean theorem to show that y is equal to 1 here. So this is 1 over square root of negative square root of 3. That's not true. That's a y equals negative 1. Y equals negative 1 is very important. So my angle x right here that I have not labeled, I want all 6 trig functions. Sine is negative 1 over 2, right? Opposite over hypotenuse, or y over r, or any of those different ways that we write them. I know the cosecant is the reciprocal. Cosine is given to me as the negative square root of 3 over 2, so without even looking at the triangle, I can find the secant of x is negative 2 over the square root of 3 and rationalize my denominator. If the tangent of x is the square root of 3 over 3, then the cotangent of x, and this is using a little cheater's method here, I know that the square root of 3 over 3 is actually 1 over the square root of 3. But if you don't recognize that, don't forget we do have this here. So cotangent of x is, cotangent is x over y, negative square root of 3 over negative 1. It's going to give me a square root of 3 over 1, which is the square root of 3. So either way you go about it, if you unrationalize, if that's even a thing, or you rationalize the numerator, it unrationalizes the denominator, or you just use your triangle, you can still find the cotangent values. Here in example 2, we have a secant of phi equals 3/2, and cosecant of phi equals -3 square root of 5 over 5. All my life I've been pronouncing that phi. Nobody's corrected me, but I thought since I'm doing this on the video and putting it on YouTube for all the world to see, I'd look it up. And my sources say that this is pronounced phi, P-H-I, phi. If you are of Greek descent or you know any Greek and you want to correct me, feel free in the comments. So the secant being positive and the cosecant being negative, this means the cosine is positive and the sine is negative. That tells me I must be in quadrant 4. The secant is the reciprocal of cosine, so my hypotenuse is 3 and my adjacent is 2, which tells me that my y value will be a negative square root of 5. Given cosecant, -3 square root of 5 over 5, I can find the reciprocal and then rationalize my denominator. I'll end up with negative square root of 5 over 3. Secant of phi is 3/2, therefore cosine of phi is 2/3. The only ones that I have to find, I have for my angle phi, tangent is y over x, or opposite over adjacent, either way, negative square root of 5 over 2. And the cotangent of phi, I find the reciprocal and rationalize. Once you use these to get the correct quadrant and draw in and label your correct values, the 6 trig functions are really easy to find if you let them be. Alright, so now we're going to get into more simplifying. And this time, we don't have a right-hand side to guide us. So to simplify, a trigonometric expression means to make smaller or make easier. If I give you tangent of x times the cosecant of x and I could use one trig function instead, well, that would be simpler or easier to do if I'm using calculus, if I'm evaluating, if I'm doing any number of things. So simplifying trigonometric expressions is a very, very, very valuable skill. When in doubt, stick with the big three and the big three: sine, cosine, and tangent. So I start with tangent of x, cosecant of x. That's all I have. And the first thing I do is I rewrite cosecant of x as 1 over sine of x, and my reciprocal identity. Alright, tangent of x times the sine of x. Well, that gives me an idea. Well, if I have a sine of x here, what's tangent of x? Tangent of x is sine of x over cosine of x, quotient identity, times 1 over sine of x, but look at that. Isn't that handy? How the sine of x will cancel the sine of x. I end up with 1 over cosine of x, which I know a reciprocal identity is secant of x. Don't overthink it. Go one at a time. Make one trade or one substitution at a time, and you can kind of watch it develop in front of you. Simplify the trigonometric expression, 1 minus cosine squared of x times the cosecant of x. Again, we always think about the basic identities we already know, and I see a 1 with a square, I'm automatically thinking of a Pythagorean identity, and my Pythagorean identity is sine squared of u plus cosine squared of u equals 1. My little 2's just don't work out very well, do they? And in this identity, we can solve, right? Subtract cosine squared of u from both sides. Oh, that 1 minus cosine squared of x, that will equal sine squared of x. So that's my first substitution. 1 minus cosine squared of x, I replace it with sine squared of x. And I leave the cosecant of x. That's going to guide to what I need. Here I have a couple of sines, so let's rewrite cosecant of x in its reciprocal identity. Sine squared of x times 1 over a sine of x. I am going to write down here as sine squared of x over sine of x. And sine squared of x divided by sine of x is a single sine of x. Think about it like this. Would you rather do work with this expression, 1 minus cosine squared of x all times cosecant of x, or would you rather just deal with sine of x? This is the value of being able to simplify trig expressions. Secant to the 4th x minus tangent to the 4th x. I have no idea what to do other than big powers I should factor. And I'm thinking of y to the 4th as y squared squared, right? That type of idea. So a secant to the 4th, that's the secant squared of x all squared, and tangent to the 4th is tan squared of x all squared. This is a difference of squares. Secant squared x minus tangent squared x times secant squared x plus tangent squared x. But once again, I have a squares coming in my head, so I know that tangent squared x plus 1 equals secant squared x, my Pythagorean identity. And so here I have a secant squared x. I'm going to replace it with a 1 plus tangent of squared x. Here I have a secant squared x. I'm going to replace it with 1 plus tangent squared of x. Tangents cancel and I'm left with a 1. Tangents add. I have 1 plus 2 tangent squared of x times 1. So that's my answer. I went from something involving powers of 4 and 2 different trig functions, one for which we don't even have a button on our calculator, we have to use a reciprocal identity, down to something simple involving only a tangent. We can handle that. If we're simplifying sine of x times the cotangent of negative x, I see in the negative, so I'm automatically thinking about even and odd identities. I know that cotangent is an odd function, so the cotangent of negative x is negative cotangent of x. I still have my sine of x out in front. That gives me the idea that maybe I should write cotangent in terms of minus cosine of x and sine of x. The sine of x is cancel out. I'm left with minus cosine of x. Much easier to find. It doesn't involve a negative angle, and it doesn't involve 2 or multiple trigonometric functions. Cosecant of theta over the secant of theta. When in doubt, let's use sine and cosine. I know that the cosecant of theta is 1 over sine of theta. The secant of theta is 1 over cosine of theta. I'm not sure I said that right. It all sounds the same in my head. Cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. But we all know that dividing by a fraction is the same as multiplying by its reciprocal. So if I multiply my fractions, I multiply straight across. I have cosine of theta over sine of theta, which is cotangent of theta. Done. And finally, this one, I give this example so many times, I don't know why. I think it's because it has a beta, and beta is always my favorite Greek letter to write. Strategy that will always work is go with the building blocks of sine and cosine. I do this differently, I believe, on the board in my lecture classes, and keep in mind with all of these examples, this is just one way. As long as you make correct substitutions, there are a lot of different ways to simplify, meaning there's a lot of different ways to do the middle steps, but you should always end up with the same thing. If it's simplified correctly, it'll always simplify down to the same, quote, answer, even if you go about it in different steps. It's just like you're walking from your dorm to the cafeteria. Somebody else might take a different route from the same place, but you're both going to end up there with food. So sine of beta tangent of beta plus cosine of beta. I'm going to rewrite everything in terms of sine and cosine. So sine of beta tangent of beta gives me sine of beta times sine beta over cosine beta. And I still have my plus cosine beta. Notice the only substitution I made was tangent as a quotient identity. But when I multiply these, I get sine squared beta over cosine beta. And here I have a cosine beta, so I put it over 1. And I notice if I'm covering up this right here, I'm looking just to the left of the arrow. If I want to add 2 fractions, I need a common denominator. Common denominator leads me to multiplying this fraction, cosine of beta over 1, by cosine beta over cosine beta, right, form of 1. That gives me cosine squared beta over cosine beta. In finding a common denominator, what I've found is, hey, look at that. I have a Pythagorean identity. Once I have a common denominator, I add the numerators, keep the denominator. But I know sine squared beta plus cosine squared beta is 1. And I know that 1 over cosine beta is secant of beta. So I've taken this mess involving 3 trig functions, and I've simplified it down to secant of beta. Well, that's some of the examples for now. Using trig identities is just getting familiar with them. Write them all down, work with them until they become second nature. Thanks for listening.